So a noise margin is between two gates because the reason we care about it is we want consistency with our digital circuits. So if we input a logical high denote green to an inverter, it'll output a logic low, which will then output in turn a logic high. And we want to maintain this consistency with respect to noise. So if we know perhaps that the minimum input voltage for a max, for it to be interpreted as a logic high, is super close to the maximum that'll output, it could be very susceptible to noise. I would say the best way to explain this is to actually go about solving this problem. So let's first look at noise margin high. And this is denoted with the equation VOH max minus V in high. So first we find VOH max, which is the maximum voltage that is outputted that is a logical high. And we go across and we look here and we see, all right, VOH max is right at VDD. What could be VDD, so we'll call it VOH max is equal to 6 volts. And let's draw that. Now V in high is a little trickier. V in high is going to be the minimum input voltage that we accept as a logical high input. And so that'll actually be outputting on this section down here. So in order to find that, we find out where the voltage transfer curve crosses or has a slope of -1. And we'll call it like right about there. And so here will be V in high. And again, this is the minimum input voltage that is accepted as a logical high and therefore corresponds to the correct output of a logical low. So we'll say, oh, that's about, I don't know, about 3.1. So then in order to solve for noise margin high, we're going to say 6 minus 3.1, and we get 2.9 volts. Great. Now, let's do the same for noise margin low. So it's first, the equation for noise margin low is similar, but a little bit different at the same time. So first let's find V in low. And so V in low is going to be the maximum input voltage that is accepted as a logical low input and will therefore correspond to a logic high output. And so again, that's where the slope crosses -1, and it's the first crossing. So V in low is there. And we'll call that 2.25. Just not quite, but just to make the math easier. And then V out low min will be the minimum value that is outputted and accepted as a logical low. So we're going to look along here and say, okay, the minimum value that's outputted as a logical low is about 0.5 volts. So V out low min is equal to 0.5 volts. A little bit of math, minus 0.5, and we get our noise margin low is equal to 1.75 volts. And that means that these two gates are compatible together because both the noise margin high and noise margin low are positive numbers. For instance, if they were negative, it would mean that maybe the transfer curve isn't quite as good and it's outputting too high a voltage to ever get accepted as a true logical low, and then they just aren't compatible, and we could have errors where it's like, oh, we output green, or we input green to the first inverter and it works as well as it can work, but then we get to the second one and it's like, oh, I don't know what that is, red, and then, or perhaps purple because it's undefined. And then what is VM? VM is actually probably one of the simplest things. VM is going to be where V in is equal to V out. Right, so if we're drawing a line, that's 1 volt, that's 2, where's 3, like this. So, all right, right here's VM. And what that tells us is kind of just right in the middle of the undefined logic zone. So we would call undefined logic anywhere between V, I, L. VM is smack dab in the middle, and VIH. And that corresponds to anywhere along this line, and VM just happens to be right in the middle.